Hey everyone, this is your pre-recorded stats lesson for this week, Thursday. We're going to finish up the linear regression section by taking a look at multiple regression. So this is going to tie into hopefully the lab that you guys did this week, looking at the nonlinear models and multiple regression. We're going to kind of go back, kind of take a look at that lab along the way and kind of show you how to interpret some of the values that Microsoft Excel is going to give. So the idea for this particular lesson is to kind of set up a linear model, and then we'll take a look at how to extend it and talk about other kinds of variables. So it's called a multiple variable regression, and we'll take a look at the output and try to interpret the output a little bit. So let's set up the following situation. So let's say we're interested in, I don't know, buying Mario Kart for the Nintendo Switch, for example, and we go on to eBay and we're looking at a couple different things with the online auctions. So we're going to start by taking a look at the response variable, which is the total price. And the total price here is going to include the final price. So this includes the shipping, the cost for the cartridge, etc. Now, the question that we have is it possible that the condition of the game is going to result in a higher total price? So right now we have an explanatory variable that's called condition, and we have a response variable that's called total price. And we've collected data on some other variables as well, but right now we'll take a look at the final price and the condition. Those will be the two variables we work with. But we actually are going to collect data on whether or not the online auction has a photo associated with it, as well as how long that online auction lasts in days. So we collect data from 141 auctions, and we get the following data chart here. Notice that under the condition and photo section, we're essentially going to be writing down whether or not the condition is new or used. If it's new, we're going to label it with the number 1. If it's used, we're going to label it with the number 0. And similarly with a photo. If there is a photo attached to the online auction, we'll essentially write down the number 1 to mean yes, and we'll write down the number 0 to mean no. So for example, the very first auction we looked at, the final price was $51.55. This was for a new cartridge that had a photo associated with the auction, and the online auction lasted for 3 days. So specifically looking at just the price and condition data, we could go ahead and we could create a line of best fit model. Okay, so using, let's say, Microsoft Excel, for example, we get the following linear model, 10.9x plus 42.87. So it does seem as though condition does play a part in the total price. In other words, I expect to see an increase of about $10.90 if the cartridge is a new cartridge. The $42.87 reflects our intercept. So this is if we have a used cartridge. So I expect to sell the cartridge for about $42.87 if it's used, and $42.87 plus another $10.90 if the cartridge is new. So that gets us, what, around $53 and some odd cents if the cartridge is new. However, if we kind of go back to all of the data that we collected, it may not just be the condition that is important to the sale or the final price of this cartridge. Maybe whether or not the online auction has a photo is also important to the overall selling price as well. So it's possible that both the photo as well as how long the auction lasts plays some kind of part in determining the overall price. And the question is it possible to update our original model, which is a plus bx, to account for these other variables? So right now, photo, for example, and duration, they're currently confounding variables because they're having a part, at least we think, in the overall final price of these auctions, and we want to be able to adjust the current linear model to account for some of these other variables. And we can certainly do that. What we do is we essentially extend the linear model to include as many variables as we need. So capital A still represents the intercept in some sense here, and then we have three associated slope values called b1, b2, and b3 in our particular example. But we can add as many of these as we need for as many of the confounding variables that we think are important for the model that we're using. So here x1, x2, and x3 are going to represent the different explanatory variables in the model. For us, we're going to try to extend the linear model in the following way. We're going to say x1, let that represent the condition still. x2 is going to represent whether or not there's a photo. x3 is going to represent the duration in days. Okay, and b1, b2, and b3 are the associated slope values with those particular variables. And essentially, by extending out the model like this, we can now allow Microsoft Excel to estimate these slope numbers, b1, b2, and b3. And we can still do that using a least squares kind of analysis, which is the analysis that we've been using for our regular linear model. But now we've kind of moved out of the realm of something that's easy to do by hand. So we're going to let Excel kind of deal with it, and we're going to learn how to interpret the output that Microsoft Excel will give us. Okay, so with that said, let's go ahead and I'm just going to pop this up so that I can do a little bit of writing on the screen. So in full, let's say we input all of this data into Microsoft Excel and we get the following output. What we're going to do is we're going to write out the actual linear model here using the estimates from the table. So I go to Microsoft Excel, I ask it to do a regression, I input all of the data like I did in the lab, and this is the output that we get. So what we're going to get is we're going to get some estimate numbers, and usually it comes out with the intercept at the top. So intercept here is always going to represent our A value inside of the linear model. And then each one of the variables is going to be given next. Okay, so it's going to estimate the slope values for each of the three variables next. So we're going to take this to be, let's say, b1, because this is the slope value associated with condition. We'll take this value to be b2. It's the slope value associated with whether or not we have a photo. And finally, a slope value that's associated with the duration. And if we wanted to write out the full extended linear model, we might have something like this. We might say that the estimated model is A, so 36.21. So there's our intercept, plus B1 times X1 plus B2 times X2 plus B3. In this case, I'm going to be subtracting 0.03 times X3. So here's our updated model with the intercept as 36.21 and our three slope numbers. And I can use this model to do some estimation. So for example, if I was curious about a used cartridge without a photo, so let's say we want a used cartridge, so x1 equals 0, no photo, so x2 equals 0, and maybe the duration is 3 days. I now have the ability to kind of guess at what kind of output or what kind of final selling price I should see. And all we're going to do is just sub in for our variables. So if I was curious about this particular situation, I could take my 36.21, I would add 0, right, because it's a used cartridge. without a photo. So again, I'm going to add 0, and then I'm going to subtract 0.03 times the duration. So I can still make substitutions like this, and it still is going to give me a rough estimate on what I expect to sell this cartridge for, minus 0.03 times 3. So we would expect to sell this cartridge for about $36.12. So that's the idea here, is the model gives me a way to kind of extrapolate or estimate final selling prices, as long as I know a little bit about the inputs of these variables. So let's kind of dive in a little bit more to some of these estimates and kind of get an idea of what these estimates mean. So what does B3 represent? So we're looking specifically at this one here. So this is our B2 and B1. So B3 is the slope value that's associated with the duration. So essentially, B3 is telling us that we're going to lose about 3 cents on the overall final sale for each day longer that we post this particular ad on our online auction. Okay, so B3 is basically telling us we're going to lose 3 cents on our overall final sale for each day longer we have this auction open. So in other words, it makes sense based on this slope number to choose the shortest duration auction possible. And similarly, we can interpret B1 and B2. So B2 is going to tell us that if we include a photo, then this is going to bring up our overall sell price by $1.08. So I should try to include a photo if I can, because that's only going to increase the overall price, the overall final sell price. And same with the condition. If I have a new condition cartridge, this is going to add about $5.13 to my overall final selling price. So once again, it's better to sell a new condition cartridge versus an old condition cartridge. And so the old estimate that we had for B1 was about $10.90. So in other words, using the regular model, selling a new cartridge, so if we kind of scroll back, back to our very first model that we used, which was here, the original slope value associated with condition was $10.90. So in other words, when we first started talking about the linear model, we would say that selling a new cartridge resulted in an increase of about $10.90. And in the updated model, condition now only plays a $5.13 overall increase in the final sell price. So I guess kind of one of the questions we might be curious about is, why does this estimate for B1 change from $10.90 to $5.13? Well, it's really because the other variables in question, such as the photo and the duration, actually play a part in the overall output here. So the reason we see such a drastic increase in the slope value for the condition is due to these other confounding variables playing a role in the overall selling price. The slope values also tell us what's the most important and least important part of the overall linear model that we're working with. So obviously condition, because condition is going to add $5.13 to the overall sale, is the most important role, I would say, in the total price. So condition is still important. It's as important as we thought it was with the regular one variable linear model versus the 3 variable linear model. And the duration actually plays the least importance here, right? A duration is only about a 3-cent difference per day. I would say that the duration is the least important in the model, with the photo and condition being the 2 more important pieces for this particular model. So let's jump out and maybe just compare this to what we saw in the lab this week. So here is Microsoft Excel. We had grabbed some data on the selling price in thousands for, I believe these were houses in Saskatchewan. And then we had some variables that we thought potentially played a part in the overall selling price. So for example, the square footage, how old the house was, how many acres of land came with the house, and the number of bedrooms that came with the house. And what we did is we told the Microsoft Excel to do a regression analysis on this being our response variable and all of these being our explanatory variables. And when we did that, Microsoft Excel popped out the following items here in the summary output. So of course the residuals down here at the bottom, we're not going to play around with those today. It will tell us the R squared value, which is about 87.59%. So a pretty good kind of multiple regression model here. So about 88% of the variation in the sell price is explained by the model, which is awesome. And then during the lab, I kind of highlighted these important pieces down here. So this is the output that we're curious about, the stuff that I've highlighted here. So the coefficients inside that coefficients column is Microsoft Excel attempting to get the estimations for the slope value as well as the intercept number. So I've labeled over on the side that usually the intercept comes first. That's going to be our capital A in the model. And then I labeled all of the others as x1 to x4. So the living area, for example, the age, the lot, and the number of bedrooms, they just kind of come in chronological order. So if I go to create a new linear model like we did in the notes from the lesson, we get something like A plus slope number times x1 plus slope number times x2, etc., etc. Here we have four variables, x1 to x4. And underneath here, also highlighted in yellow, I just went ahead and actually wrote out that linear model, starting with the intercept, so 1.09, plus the slope value associated with the living area, minus the slope value associated with the age, etc., etc. So instead of just looking at a linear model a plus bx, I've extended it and looked at it like this. And what this essentially allows us to do now is extrapolate to try to figure out what the sell price is going to be for a house with certain parameters. So let's say, for example, I wanted to calculate what I think the sell price is going to be for square footage of, I don't know, 1,500. Let's say the age of the house is 20 years. The lot size is maybe 2,200. I think that was a reasonable, or sorry, it's in acres. I have to be careful here. So let's go 2.2 acres. And the number of bedrooms, number of beds. Let's take that to be, it's 1,500. Let's take 2. So if I have this information, I can now ask Microsoft Excel to extrapolate this data by just kind of doing a formula like this. So we're going to look at our equation we have for y hat. So 109.06 plus, okay, slope number times square footage plus age times 20 plus slope number for lot size times lot size plus number of bedrooms slope value times 2. So getting Microsoft Excel to do this multiplication for us using that formula that we created, we should get a pretty good estimate on how much we're going to be able to sell this house for in Saskatchewan. So a house with this kind of parameter should sell for about $284,000 and some change. So that's kind of the idea with the multiple model, is it is better at accounting for some of these confounding variables and allows us to do extrapolation when there's several variables involved instead of just one. So this is a kind of a very typical thing that you would see working with actual experiments and actual studies. Now we can take a look also at these slope values and try to determine what these numbers mean. So what does the 109.06 mean? It means that this is kind of like our starting base price. It's hard to interpret this one because we're probably not going to find a house that has 0 square feet living area, 0 age in years, 0 lot size, and 0 bedrooms. But this is kind of like our starting base price. And everything either gets added or subtracted from this starting base price. So a little harder to interpret this one because we can't put zeros in for all of our x's. But we can interpret some of these other slope values. And the number of bedrooms, I think, is probably the most important one here. So 33.6. So this is saying that as the number of bedrooms increases, I expect to see about a $33,000 increase to my overall sell price per bedroom, which is pretty intense, right? So the bedrooms is kind of important. And not really that surprising in the housing market in general. When it comes to the lot size, for each acre that we add to the lot size, we're expecting to see an increase of about $13.5 thousand to our overall sale. And of interest here too is that the age in years also has a little bit of an effect, but in the negative direction. So we expect to see about a $0.75 thousand. So this is what, about $750 decrease per year that the house has been around. So that's interpreting some of these slope values and understanding how we can use the overall model to get some guesses at how our final sell price is going to look like. Hopefully that makes sense. Now, the last part I want to just quickly chat about is in class on Tuesday, we talked about the R-squared value. And the R-squared value essentially tells us the proportion of the variation that's explained by the linear model. And we can take the R-squared value that we saw on Tuesday and adjust it for multiple regression. So this is the R-squared valued as is. And if we multiply the usual R-squared value by a fraction of n minus 1 over n minus k minus 1, then this will adjust the usual R-squared value to be one that we can use for multiple regression. So this is something that Microsoft Excel does do automatically for us. So my recommendation is to just have Microsoft Excel do the regression, and we're going to find the R-squared value right here. So this 0.8759, this is going to be the R-squared value using Microsoft Excel. We unfortunately won't be able to do it using our calculator unless we have some more information. Okay. So, I mean, the information we would need is the RSS and the TSS, so our residual sum of squares as well as our total sum of squares. So those things are hard to get by hand. But it is possible, if we have that, to actually calculate the adjusted R-squared by just subbing in some of our values here. Okay, so our RSS is 23.34, the TSS 83.06, and then we need to multiply by the numbers here. So n is equal to 141. This is the total number of online sales that we looked at, so our number of data points. Okay, here k is equal to 3 because we looked at 3 different estimates or 3 different variables. Okay, so we calculated 3 different slope values. So the fraction we need to multiply this RSS over TSS by is going to be 141 minus 1 over 141 minus 3 minus 1. So I believe that's going to be 97. 137. So 140 minus 3, yeah, 137. Okay, and the R-squared that I get after simplifying is about 0.7128. Okay, and that's going to finish off the class for us. This is connected to chapter 4.1 of the textbook. So please take a little peek at the textbook if you want a couple more examples or maybe some practice questions to work on at the end of the class there. And of course, if you guys have any questions over the reading week, please do not hesitate to send me an email and let me know how you guys are doing. So have a great reading week. Remember that the Section 2 test is going to be coming up. It's due on, I believe, the 21st of February. So you should be able to start working away at that Section 2 test after you've watched this lecture and done a little bit of practice. And you can go online and get a kind of a sample of the style of questions that you might get asked inside of Section 2 on Moodle. Okay, and like I said, the Section 2 test will be due on by the 21st of February. So start working away at that when you get a chance. And I will be around, so just email me if you have any questions. All right, talk to you later, guys. Bye.